Hey, everybody. We are going to take a look at more exponential growth and decay today, but in a little bit different context. I think there's probably some questions from the assignment that is due on Wednesday. And I think some of those questions might be answered by what I'm going to do now. If not, we can certainly talk about them on Thursday. But let's take a look at what we're doing today. All right, we're going to take a look at growth and decay models. That is the topic of the day. When I do these video asynchronous lessons, I'll go at a fairly rapid pace so that the video doesn't get to be too long, especially because you will be able to pause and rewind and go back and look at things if you need to. Here is our formula. This is our second main formula we saw yesterday. Y equals A times B to the X. And even though these letters are completely different, I'm going to make the claim that this is basically the same equation. Now, instead of y, we've got a equals, but that just stands for some final amount, the output of our function, if you will. And so the final amount is equal to the initial amount or the starting amount. That was our y-intercept for the previous version of this formula. This 1 plus r looks more complicated. But I will say that 1 plus r, we can think of that as our multiplier. So we can think of that kind of like we thought of b in the previous formula. And you're going to have to bear with me. I am writing with my mouse, so it'll be a little bit more sloppy than we might be used to. Oof. Our multiplier of 1 plus r. So if something is doubling, we can think of that like it's got a growth rate of 100%. And then our growth rate of 100% is represented with 1, and 1 plus 1 is 2, and so we multiply by 2. Usually when I hear doubling, I just think multiply by 2, tripling, multiplying by 3. But we could think of it as a growth rate of 100% or 200% or whatever it is. And then instead of x, we've got t. And the letter T is used for what we're doing now because T can stand for time. Now, I've got written the number of time intervals, and this is something that maybe came up in the assignment that was due on Wednesday, because sometimes the number of time intervals wasn't necessarily the amount of time. It was, maybe the growth that you were learning about or thinking about was a 2-month time interval. And so if I look at 1 year, 1 year would represent 6 2-month time intervals. And so we'd have to think about doubling in a certain amount of time and how many of those intervals there are. Just a quick word about this growth rate. It could be a negative number. Our multiplier is 1 plus that growth rate. So for some quick examples, if I've got 50% growth, that 50% growth would be the same thing as an R value of 0.5. 50% is the same thing as 0.5. Moving that decimal place over 2 spots, so 50%, move that decimal place over and call that 0.5. And then our multiplier from that equation, 1 plus that growth rate of 0.5, we'll call that just 1.5. And if we think about it in terms of these problems, okay, 50% growth means that it increases by half, and increasing by half would be the same thing as multiplying by 1.5, the original plus that extra 50%. 25% decay, well, then we're going to think of our growth rate as negative 0.25, negative because our amount is decreasing, and you're thinking, well, that doesn't make sense. We're going to get negative values. Remember that our growth rate is negative, but in our formula, we've got 1 plus that growth rate, which is going to look a lot like 1 minus 0.25%, which gives us 0.75. An alternative way of thinking about this is that if I've got 25% decay, if I'm losing 25% of something, then I still have 75% of it left. So a multiplier of 0.75 would correspond to decay of 0.25. When we get into smaller numbers, 0.5% decay, well, again, negative because we're looking at decay. And then 0.0, 0.00, well, move that decimal place over. Right now it's 0.5. So if I move that decimal point over 2 spots, we're going to have 0.005 for our growth rate, negative 0.005, which means my multiplier will be 0.995. If 0.5% is gone, then 99.5% is still there. And then, as I mentioned before, 100% growth corresponds to a growth rate of 1.00. And so your multiplier would be 2. So 100% growth is doubling. A few examples that I'd like to go through. I've got one example here where my car is decreasing in value by 20% each year. I want to know what is the value of the car in 5 years if today my car is worth $8,000. So we'll gather the information on this slide and then we'll actually get some numbers on the next one. Growth or decay, well, we've got decreasing value, so this is going to be a decay model. My car, sadly, is losing value. My multiplier, well, if it's decreasing by 20%, that means that my R value is negative 0.2. And so my multiplier will be 0.8. Once again, if my car loses 20% of its value, then it still has 80% of what the value was. And my starting amount in this case, pretty clear, $8,000 for the value of the car today. So my equation, the equation that models my car's value is that, let's see, I'm going to use V to stand for the value. If you want to go by the formula from the beginning of this week, you might say Y equals if you want to do everything in terms of X's and Y's. If you want to go strictly with the formula that I've got here, you could say that A, the amount that the car is worth, but I'm going to say V. It stands for the value of my car. It is going to be my starting amount, 8,000, times my multiplier, 0.8, from that 20% decay, raised to the power of T, where in this case it's going down by 20% each year. T is the number of years. And so if I want to find the value of my car in 5 years, I'll just plug 5 into that. I went ahead and did this before starting the video, and when I plugged 5 in for T, I got a value in 5 years of $2,621.44. And this is maybe a good time for me to mention, if you've got a question that's asking for a value of something in dollars, let's go ahead and round to the nearest cent. I don't think it makes sense to go past the nearest cent. Pardon the pun. And even though when we're talking about cars, we usually don't think about the value in cents, but let's just go with that as a rule of thumb. Round your money answers to the nearest cent. All right. Again, I'll go fairly quickly. If you need to go back and rewatch something, you can certainly do that. Otherwise, I'm going to keep on rolling. My second example, when I graduated from high school back in the 1900s, the average price of a movie ticket was $4.35. Wouldn't that be great? I did a little bit of calculating, and I estimate that the value of the price of a movie ticket has increased by about 3.08% every year since then. Of course, it changes over time, but I'll go with an average of 3.08%. And so find the average price of a movie ticket today, and also predict the price of a movie ticket in 20 years. So our situation here, the value of movie tickets is increasing, so we'll go with growth for this one. Increasing by 3.08 means that I'm going to have an R value, my growth rate, let's see, 3.08%. Move that decimal place over a couple of spots. We're going to have 0.0308. Since we've got growth, we'll have 1 plus that, so 1.0308 will be my multiplier. And my starting amount, I guess I'm saying that the year 1995 is my starting year, so I can use my starting amount of $4.35, $4.35. This is a little bit unusual to say that 1995 is my time equals 0. I'll have to take that into account as I think about what the year 2021 is and what 20 years from now is going to be. but that'll come in my equation. My equation is going to be, let's see, I'll go with C. The cost of a movie ticket is equal to my starting amount, $4.35, times my multiplier was 1.0308 to the power of, well, I'll go with T for time again, where time is the number of years after 1995. Now, some people, when they do problems like this, they'll say something like, I'm not sure why I erased that. They'll say T minus 1995. That way, when they plug in the year is 2021. And so when I plug in 2021, 2021 minus 1995 tells us that it's 26 years. And I'm okay with that, but that also makes our formula a little bit more complicated. And also, we're not maybe thinking as much about what this T represents. So I'm going to say that 1995 is year 0. Go ahead, if you want to use that other more complicated formula, go for that. I guess I don't have a spot for our value now. So I'll add that. The value of a movie ticket now. Well, I'm going to plug in T equals, if 1995 is year 0, then 2021 is 26 years. I know this because I just went to my 26th year anniversary or class reunion a few months ago. And so the number of years that we're talking about is 26 years. When I plugged that into my equation, 4.35 times 1.0308 to the 26th power, I got the price of a movie ticket, and this is actually fairly accurate, I believe, to be a little bit less than $10, $9.57. And if you're saying that looks extremely low, that maybe means that you go to a lot of evening movies where you pay full price, or maybe even 3D movies where you pay $15 or something like that. But average price of a ticket, about 9.57. And then if I want to do in 20 years, well, I'm not going to plug in 20 because that would be 20 years after 1995. That would be 2015. I want to look at the value of a ticket 20 years from now. So if I was with you in class, I would pause and I would say, what am I going to plug in for T? And someone would hopefully eventually raise their hand and say that if right now, if 2021 is 26 years after 1995, then 20 years from now would be 46 years after 1995. And when I plugged that into my equation, I got the cost of a ticket to be an eye-opening $17.56. Again, rounding to the nearest cent for these money type of problems. When you're plugging these numbers into your calculator, 1.0308 to the 46 power, it's a weird looking number, and it's got a whole bunch of decimals to it. Multiply that by 4.35, and then finally at the very end, when you get to your answer, round that to the nearest cent. And then final example for this video asynchronous lesson. Population of Burnsville in the year 2010 was 60,306. 4 years later, it was a little bit more than that, 61,630. And so if you look at the growth over that time period and divide by how long it took, you'll get a growth rate of about 0.54%. I rounded it to 1/100th of a percent. And we'll see that this makes for a little bit of rounding error, but I'm going to go with 0.54%. Assuming the population continues to grow at the same rate, predict the population in 2050. So same situation. We're looking at growth again. The population of Burnsville, at least on that time interval, was growing. I'm not sure if that's still the case. The population of young people is decreasing, but I think that's because we've got an aging population. But I'm going off on a tangent, and we don't need to worry about that. Growth rate of 0.54% means that my R value that I would plug into my formula is, well, let's see, move that decimal place over a couple spots, 0.0054, which means my multiplier is 1.0054, 1 plus my growth rate. And my starting amount, this one's a little bit open for interpretation. If I want to say that my starting year is 2010, I might use 60,306. Again, if I do that, then I'm saying that 2010 is year 0 in the scenario, but I could also interpret this to be that 630 is my starting amount. And if that's the case, 2014 is year 0, and both of these are going to work. We'll see that we get a little bit of rounding error depending on which one we do, but I'll show that on this next slide. My equation. Well, I guess I've got two different possible equations. If I want to say that the population at time equals 0 is 60,306, I'll use 60306 times 1.0054 to the t power. Or if I want to say that the year 2014 is my year 0, then my population starts at 61,300. Excuse me, I'm not sure. I must be slightly dyslexic on this number. 61,630 times 1.0054 to the t power. Now, if I use the top equation, if I'm looking for the population in 2050, I'm going to use time equals, let's see, if year 0 is 2010, then year 2050 would be year 40, and I would plug in time equals 40. If I choose to use this form of the equation, then 2050 is, let's see, a little bit less. 2014 is 4 years later, so I guess I'd be using time equals 36. 2050 is 36 years after 2014. And when I do this, I get two slightly different numbers. Again, I plugged these into my calculator already. In a case of population, whether we're talking about monkeys in the assignment that was due today or people living in Burnsville, I'm going to round my answers here to the nearest person. So using the first model, starting in 2010, I get 74,802. Using the second model, I get 74,800 and, oops, sorry about that, 816. Using time equals 36 and the different starting value. And we can see there's a little bit of rounding error because I'm using 0.54%. It was probably more like 0.5386 or something like that. And I just rounded that off, and that rounding off gives me a little bit of error. I'm off. My two answers are differing from each other by about 14 people, and that's okay. If I'm going to be picky about this, then I'll make sure that I state which of these is supposed to be your year 0. Anyway, there we go. I suppose I'll wrap things up. I'm not going to switch back to my video. You guys know what I look like. But take a look at these problems, work on these, and if there are questions over the assignment that was due on Wednesday or this assignment that'll be due on Thursday, we can talk about those when we see each other again in class on Thursday. Have a great day or have a great evening, and I will see you on Thursday.